Now we're trying to put everything we know about synthetic division all into a useful tool set. The first thing I'd like you to do is pause the video and read the historical note and the rational root theorem and the fundamental theorem of algebra. Now pause the video and read this section, the rational root theorem, in practice. Now, let's put it into use. So I'm going to do a problem here. I'm going to talk a little bit more about how we make this possible list of roots on the second problem. But for here, what we're supposed to do is to look at the constant, the number at the end. So that would be this plus 6. And I'm going to list everything that can go into a 6. It could be a 1 or a 2 or a 3 or a 6. And that's all that can go into a 6. Now, I'm going to put a plus or minus on that list because I'm not sure whether the solution numbers are going to be positives or negatives. And I have to take into account that that's the possible rational roots. Now, the next thing it says that we're going to do is to divide that list by anything that goes into the leading coefficient over here. Well, that leading coefficient, the coefficient of the x cubed, is simply a 1. And dividing by 1 won't change value, so my list is complete. Now, the next thing that I do is to type the equation into my y equal of a TI-84. And I've already done that for myself to save a little time. Now, the smallest and possible roots that we could possibly have would be positive or negative 6. In my window, I'm going to set my minimum, one left of negative 6, negative 7, one right of positive 6, positive 7. Now, leave your scales at 1. That puts the tick marks on your x-axis. And then the next thing I want to do, probably, you don't have to do this, I like to change my y min, y max to a negative 30 and a positive 30. And I like to zero the scale on the y's. And we'll talk about that more in class, but it's just a good practice and you'll get used to it. Now I look at the graph and I see a graph there. The reason I wanted the ticks on the graph is it looks to me like there might be a solution there at x value negative 2. I hit the trace key and I don't move the cursor around. I simply type in negative 2 and press enter. And I can see here that if I input negative 2, the output is a 0. That tells me I've found a solution. So that's what I'm going to do, is to take that negative 2 number, x equal negative 2, and I'm going to go and do a synthetic division with x equal negative 2. I feel safe in writing down my first solution. My first solution, x equal negative 2. Now, one of the things that you should recognize is that indicates that there's a factor that is an x minus 2 equals 0. Now, let's do a synthetic division, and we have 1x cubed, 0x squared, minus 1x's, and a plus 6. And we're going to do a synthetic divisor of, of a negative 2. So the factor, would have been an x plus 2. So here's the synthetic division. Drop the 1, multiply, negative 2, add, negative 2. Multiply, positive 4, add, positive 3. Multiply, negative 6, add, 0. Now you might have noticed on that graph that it only crossed the axis one time, but that doesn't excuse me from finding all the zeros. So we're going to solve. It said solve the equation. We're not done yet. Now the first thing we should do is to correlate our synthetic division table to the factoring of our polynomial. So the x minus 2, the negative 2 solution value indicates an x plus 2 factor. And the other factor would be x squared minus 2x plus 3. And all of that would still be the equation equal to 0. How do you solve polynomial equations? You set them equal to 0, which was already done for us. You factor them, that's what we just did. And then you set each factor to 0 and solve. Now notice, first of all, that we've already solved this one. This is the x equal -2 we saw in our graph. But how do we solve this second one? Well, we have to try to factor it, but it can't. And you should recognize that quickly. So we're going to go to the complete the square method. So we're going to move the 3 to the other side by subtracting 3 from both sides. We're going to add the term of completion. And the term of completion is based on the idea that there's some binomial that squares to make x squared minus 2x plus something else. That's the x minus 1 binomial. When I expand it, square the first, x squared, multiply and double, -2x, square the second. I like to change colors just to remind you that that plus 1 has to be added to both sides, but that plus 1 is what makes the three-termed expression equivalent to the binomial squared. On the other side, -3 plus 1 is -2. So we take the square root of both sides, and whenever we take square root in equation work, don't forget there's always an understood plus minus there. So x minus 1 is equal to plus or minus, well, the square root of a negative is an imaginary. And then we add 1 to the other side, and x is equal to 1 plus or minus I square root of 2. That's how you do it. So I've found my three solutions. My three solutions are x equal -2, and x is equal to 1 plus I squared of 2, or x is equal to 1 subtract I squared of 2. Now, on this next one, I'm going to try to give you a little better sense why we make this list the way we do. I see a fourth power polynomial here, and I suspect that that fourth power polynomial could break down into 4 separate factors. And my thinking is that when I multiply these last terms together, they eventually have to multiply together to equal 4. Well, what could do that? Well, it could be a 4 and a 1 and a 1 and a 1. Or it could be a 2 times a 2 to make the 4, but then we'd still have to have a couple of 1s, otherwise the product would be bigger than 4. So what possible numbers might we have for that term there? So we could have an x plus 2 binomial, but we don't know if it's plus 2 or minus 2. And if we had an x plus 2 equal to 0, or if we had an x minus 2 equal to 0, that's where we would have solutions of plus or minus 0, or plus or minus 2 rather. And if I had a factor of an x with a 1, I don't know if it would be x plus 1 or x minus 1, but when I set the factors equal to 0, I would have solutions of either positive 1 or negative 1. That's why I put the 1 and the 2 in that list. But remember, one of the other possibilities was there could have been a 4 there, and that's why I also include that 4 there, and that's why I put the little plus minus there. Now, the next thing that I have to realize is this. Not only do those last terms have to create the 4, the first terms have to create a 6. Well, what does that mean? Well, maybe one of those factors was a 6x with a 1. And if one of those factors was a 6x with a 1, then that would indicate to me that there might have been 6x plus 1 or a 6x minus 1, either one. And I would set that equal to 0. And if I did that, then that would give me an eventual solution of either negative or positive 1/6. But by the same token, maybe to make that 6, what I had was a 2 and a 3, like a 3 right here and a 2 right over here. And so I could see solutions of plus or minus 4/3. I could see solutions like plus or minus 1/2. So whatever makes that 6 eventually becomes the coefficient of x in your linear factor, and therefore eventually becomes the denominator in your solution. Now, in practice, what we do after we've made that list of numbers that goes into our constant at the end, in this case the 4, I go back through and I make a list in my head of everything that goes into a 6. It could be a 1, or a 2, or a 3, or a 6. So I'm going to take that 1 and imagine dividing it by 6. I should make this box a little bigger, I think. I'll do that before I print it for you. So I could either have plus or minus 1 over 2, or I could have plus or minus 2 over 2, or I could have plus or minus 4 over 2. Now notice this general rule, that if you can reduce the fraction, it's already in your list. So I don't need to list these two, but I'll list them here. But you just tell yourself if it's already in the list, you don't need to include it again. So I'm now going to take everything in that whole number list, the 1, 2, and the 4, and divide it by a 3. So I could have either a 1 over 3, a 2 over a 3, or a 4 over a 3. And you'd notice that all of these numbers are new numbers to the list. And then I'm going to do it again, this time with the 6. So I could either have a plus or minus 1 over 6, 2 over 6, or 4 over 6. And you should notice that as I wrote those, the 2 over 6 is a third, and it's already in the list. And the 4 over 6 is 2/3, and that's also already in the list. So with that in mind, there's the list of possible rational roots. Now, just like the last time, we're going to go to our calculator and we're going to put in the equation. So I've already put that second equation in for convenience. So I'll reactivate that second equation. And again, I noticed that the biggest impossible numbers that I might have as solutions are positive and negative 4. So I'm going to set my x min x max to a positive or negative 5. And I'll leave that negative 30, positive 30 there, and those ticks at 1 on my x scale are extremely important because they allow me to make estimates. So let's look at our graph and see what we see. Well, it looks like it might cross the axis somewhere between 0 and negative 1. So we look at our list of candidates to see if there's any numbers there. Well, I see that it could be maybe a negative 1/2. So let's see. Is negative 1/2, and I just do it as a simple division, is negative 1/2 a solution number? No, it's not. It didn't equal 0. Well, there's another number, negative 2/3. So let's try negative 2/3 and see what happens there. Look, that's a solution number. So I'm going to go back to my work, and I'm going to tell myself right now that x equals negative 2/3 is one of my solution numbers. But let's go back and look at the graph. I see that there's also an apparent solution number somewhere between 0 and 1. It looks like about halfway there. And I notice that 1/2 is one of the possible solutions in my list. So I'm going to see what happens at x value 1/2. And that's also a solution. So I'm going to go back to my work and write x is equal to 1/2. Those are solution numbers. Now, there is one other number that appears to be about a 2 point something, nearly a 3. Is there any list in my number, in my solution possibilities, that would be around a 2 point something, nearly a 3? And there is not. So I'm done with that work. I don't need to look anymore, but I have made the notes that I need to make. So now, back to the synthetic division. We're going to set up our synthetic division problem, and we're going to put all our coefficients, 6, a minus 11, a minus 16, a 2, and a 4, and we're going to take out that negative 2/3 first. Now it looks a little scary, but don't worry, it's going to be perfectly friendly. So drop the 6. Negative 2/3 times 6, well, 3 cancels into 6 twice, and negative 2 times 2 is negative 4. Now, add the column negative 15. Negative 2/3 times negative 15, well, negative times negative is positive. 3 cancels into 15, 5, and 5 times 2 is 10. Now add the column negative 6. And then negative 2/3 times negative 6 would be positive 4. We did that problem just a second ago, as a matter of fact. When we add our columns, again, we get a 6. And we know that negative times positive is negative. And there's that 2/3 times 6 one more time, giving a 0 remainder. Now, at this point, we should go ahead and write that this is actually x plus 2/3 as a factor times, and watch real carefully what I do here. I know that that's actually a 6, since these were x to the 4th, that this 6 here is an x cubed. But did you notice that each term in this depressed polynomial here is divisible by 3? So I'm going to factor out that 3. And when I factor out that 3, I would then not have 6, but 6 divided by 3 is 2x cubed. And then 15 divided by 3 is 5x squared. And negative 6 divided by 3 is minus 2x. And then 6 divided by 3 is 2. Now, at the same time that I do that, I'm going to distribute this 3 into this parenthesis there, so that I would now see my factors as being 3x plus 2, not 3x plus 2, yes, 3x plus 2, times 2x cubed minus 5x squared minus 2x plus 2. Now, my second solution that I found on the graph was x equal half. So I'm going to look at this depressed polynomial, pull its coefficients out, 2 minus 5 minus 2, 2. And I'm going to do a synthetic division, this time with my 1/2. And again, don't worry, it's going to work out just nice. So drop the 2, half of 2 is 1, add the column negative 4. Half of negative 4 is negative 2, add the column negative 4. And then half of negative 4 is negative 2, add the column 0, which is what I expected. And so now I'm going to see one more time that this 1/2 synthetic divisor actually corresponds to an x minus a half factor. And I'm going to factor the 2 off of the 2x squared minus 4x minus 4 and distribute it into there. And you're going to have to follow closely to notice all that's happening here. I'm going to still have my 3x plus 2 factored from the previous step. And remember, this is just a factoring technique. So we carry those factors forward. And instead of having the x minus a half, I know that I'm going to be able to factor the 2 out of this and distribute into the other factor. So instead of x minus a half, I'm going to distribute a 2 in there and have a 2x minus 1. But I factored the 2 out of the 2x squared minus 4x minus 4. So I'm going to have an x squared minus 2x minus 2. And all of that is my equation equal to 0. So how do we solve polynomial equations? Well, we set them equal to 0 and factor them, and then we take each factor and set it equal to 0. Now, this may seem redundant to you, but I think it's good practice. Just kind of internalize those processes. Let me zoom in on it a little bit so it maybe is a little more apparent. I'm setting each of my factors to 0. And the reason I'd say it might seem redundant is that we already knew that this solution here was a negative 2/3. We found it on the graph. And we already knew that this solution here was in 1/2. We already found it on the graph. We used those in our synthetic division a moment ago. But what about this third one? So this would give us an x squared minus a 2x minus a 2 equal to a 0. And it won't factor, so we're going to do the complete the square technique again. We'll add that 2 to the other side. And then this is so similar to the one we just did. It needs a term of completion of a plus 1, making this a 3. So we'll take the square root of both sides, and we'll have now an x minus 1 equal plus or minus square root of 3. giving us a final solution of x is equal to 1 plus or minus square root of 3. Those other two numbers that were on our graph that we couldn't reconcile are those two irrational numbers, 1 plus the square root of 3 and 1 minus the square root of 3. One of the things that you can do, it's definitely not a requirement, but you can go back to your calculator and in your trace function, you can input what we think we have just found. So on the calculator, I think that 1 subtract a square root of 3 should be a 0. So let's see if it is. Yeah, look, it is. Y equals 0. And we also thought that 1 plus a square root 3 would be the other solution. So let's see if that is a solution. Now, one of the things that oftentimes happens on these is that you might get like a 1e negative 12, negative 13, negative 14, and that's just decimal round off error. But notice that I've confirmed all 4 of my solution numbers on that graph. Well, that's how you do it.